Hello, we are Group 3 and this is our progress update video. Our presentation will be divided into parts to better explain our achievements, what we have done so far and what we will do going forward. So first, I want to introduce our team members. We divided our team into different roles so that we can further increase our efficiency and meet our deadlines. First, we have our project leader, Andrew. Our equipment manager is Volkan, and our communications manager is me, Demir, and our driver is Aaron. Then we have sub-teams so that we can divide our tasks. We have our coding team, which includes me, Adi, Andrew, Aaron, and Volkan. And then we have our driving strategy team, which includes Oli and Milan. For our tests, we decided to divide our entire group. So our air resistance tests will be are done by Volkan and Adi, and our rolling resistance test is done by Oli and I, and our dynamometer test is done by Milan, Andrew, and Aaron. So to introduce our project. We've been given a task by EP Vehicles to develop a passenger car that is fully electric and energy efficient. Our personal goal is to find an optimal driving strategy in order to increase the car's energy efficiency while maintaining comfort of a city passenger car. Our requirements for this are a speed measurement system that shows us when we are at our optimal speed and help us with our driving strategy, a toll payment system to track our car's lap time and how many laps is done, and a cruise control system in order to maintain our designated speeds and that is able to deactivate upon deacceleration. So our group's approach for this to be possible, we decided to do a tank-to-wheel analysis, gathering results like the coefficient of drag and resistance, rolling resistance, and building an optimal design for our car to be efficient was some of these steps. First, our colleague will help us explain how we did the air drag test.
Hello, my name is Volkan. I'm part of the test group aerodynamics and air drag testing. Our objective as a team is to get the most aerodynamic configuration possible for the model car. For the past couple of weeks, we have been working on the test plans. So as a whole group, we have done wind tunnel tests, dynamometer tests, and rolling resistance tests. But now I'm going to talk about the wind tunnel tests. When designing an energy efficient electric car, every detail matters, and aerodynamics plays a critical role in achieving optimal performance. By minimizing air resistance, we can significantly reduce the energy consumption. As for my group, which is the wind tunnel test, we first came up with the parameters for the configurations of the car because we have a lot of options to how we design the car or how we're going to use it during the test days. So we chose 3 different configurations and 3 different wind speeds that we want to test at the wind tunnel. The car's components were given to us except the bottom plate and the front wheel covers. For the bottom plate, we thought we can implement a feature. So we extended the back a little bit, and by cutting precise lines and with some tape, we made a back diffuser, and we believe that the diffuser could lead the wind better outside. And help with the aerodynamics of the car. So after the tests, we got the values. The table of measurements can be seen here. The minimum drag force that we observed was on the configuration with the bottom plate and basically every other component except the rear wing. So we decided that this is the optimal choice and we will not use the rear wing or spoiler with the car. Even though probably the spoiler makes the car grip better to the road, it increases the air drag force applied on the car, so it kinda, at optimal speeds, it kinda reduces the energy efficiency. So what I'm trying to say is our choice of driving strategy is more energy efficiency instead of speed. On this configuration, at this configuration, no rear wing, but every other component on, at close to 5 meters per second wind speed, the air drag force was close to 0.5 newtons, and with some calculations that with the formula that we've seen on the previous slide, the air drag coefficient that we got was on the optimal choice was 0.48. So finding the air drag coefficient is really important so that we can make comparisons with other things. So now that we have the numbers, our job is now to go a little more in depth and detailing the project and the tasks, how we approach the tasks we have at hand. For example, the inside of the car, the interior components, the coding, the driving strategy, the battery of the car, the energy output of the motor that's inside the car. So after, now that we've got these, we can focus on those. Thank you for listening. Now we're going to the dynamometer.
Hello, I'm Milan. I was on the dynamometer team. The goal of the dynamometer is to correlate the speed, force, and the efficiency of the vehicle, and then an efficiency map is made from these numbers. Yes, the dynamometer test measures the efficiency of the powertrain. It consisted of 3 tests. First one is a no-load measurement. This was done by disconnecting the powertrain. This was to measure the rolling resistance, and the second test was with the powertrain connected and at varying speeds. This was to measure the total power consumed by the system and the auxiliary system and the powertrain. Yes. Next one is when everything is connected, but there are no speed at 0 speed, and this is so that the auxiliary system's consumption can be measured, and then we can calculate the input power that is needed for calculating the efficiency. Okay, now the rolling resistance.
For the rolling resistance, I'll take over again. So let's start with the question, what is rolling resistance? Rolling resistance is the force that opposes motion for rolling objects, namely the tires of the car in our case. It is mainly caused by the deformation of the surface or the energy losses due to internal friction, among other reasons. As we can see, the car is affected by the weight, the driving force or the pulling force, the air resistance, and the friction, which is our rolling resistance. Our goal is understanding the coasting mechanisms, finding velocities for turning, which is important because rolling resistance is most effective at these points. And we want to use these knowledge to contribute to the development of our optimal driving strategy. So our approach was to do a coast down test. We did two versions, one with the electromotor connected and one with disconnected. The disconnected one is for finding the coefficient of rolling resistance, and the connected one is for finding a rolling resistance coefficient more close to what we will see in the test and the driving day. To be able to find the coefficient, hold on, come back. Thank you. First, we can see that the velocity goes down because of F total, which is rolling resistance, and the drag combined. We split these into two formulas, which is the normal force times the coefficient of rolling resistance, and our air drag formula is here with the fluid density of air, the coefficient, the surface area, and the velocity divided by 2. So after rearranging our equations, this gives us that the coefficient of rolling resistance can be found with this formula. The only thing we're missing here is to find the velocity, of course, and the acceleration or deceleration in our case, which is found by the change in velocity over change in time. For our test results, we have some known variables and constants, which is the weight of the car, which is 11.677, which we weighted with 4 different scales under each tire, which we also included the power supply, so we have an accurate description for our test. We have the drag force, which our colleagues have already calculated, so putting the velocity in place, you can easily find us the drag. And we have the G, which is 9.81. We have for the unknown, we have the coefficient of rolling resistance, which we're trying to find, and the acceleration, which we'll find with the test. So our test results came that the coefficient of rolling resistance at 1.655 meters per second, which we tried to get close to as possible for our 3 variable speeds, was 0.03514. And we can see that our coefficients on these two are very similar with 3697. An increase we can see in the 2.328 meters per second. And our average came to 0.0374. Again, when we continue our test, this is the results of with the motor connected, which is more reliable for our test, for test drive. We can see that there's a very dramatic increase in the coefficient of rolling resistance, which means the electromotor connection actually affects the rolling resistance in our case. Alright, so my friend will take over and show us what we will do in the next steps so far. You can take over.
Hi, I'm Adi. I'm going to present what we're going to do next. For the next couple of sessions, we will dedicate our time towards the software and system aspect of the challenge. We will work on 3 systems: a toll payment system, a speed measurement system, and a cruise control system. The toll payment system communicates wirelessly the car's identity to the toll station. It does this at every pass on the track via an IR sensor and RF communication. The speed measurement system measures the speed of the car and it indicates it via RGB LED strip. The light bar displays various patterns to show the driver the car speed. The cruise control system helps maintain the desired speed. but can also limit the maximum speed. It communicates via UART serial communication to the powertrain's control board, and it regulates the throttle until the targeted speed is reached. The system can be deactivated by decelerating. I'm going to present the driving strategy. The car is supposed to be an efficient city car, so the car should not accelerate or decelerate too quickly, because it loses a lot of energy, and in a real life situation it would be very uncomfortable. To combat this, instead of braking, we can let the car coast, so it slows down, and the car should take turns at an optimal speed to minimize slip, maintain control, but also to be as efficient as possible and to be as comfortable as possible. So in a real life situation, in a turn, you don't throw people around. Thank you for your attention.